webinar. Our today's speaker is Professor Peter Grabner from Purdue University Fort Wayne, and he will tell us about a balance for spherical codes, the Levenstein framework lifted. And please don't forget that after webinar we have some time to socialize, to talk with each other. Please.
Thank you very much, Tanya. Thank you to the organizers of this webinar. That's some really fascinating work you guys did, and I'm very happy to attend as many of these as possible. So this is a joint work with Professor Boyvalenko from the Bulgarian Academy of Science, Doug and Ed from Vanderbilt, and Maya Stoyanova from Sofia University. I want to start with a brief outline. Now, many of these things may be known to this audience, but still I have some of my colleagues chime in that don't know exactly all of this background, so I will be introducing it. And we'll go first on why minimize energy, give a brief review of various applications of the problem, and then the necessary background on minimal energy, spherical harmonics, and Gegenbauer polynomials, and introduce the Dosar-Teudin linear programming. Once we get there, I will provide some heuristics that actually I found out later after we did solve some of these problems, and then introduce the notion of university lower bound space, or ULB space, and then the Levenstein framework, which comes from maximal codes, and the main theorem in that respect, then the test functions that Boyvalenko and his students introduced in the 1990s, and we will get to the lift of the Levenstein framework. And as an important example, we will revisit the universality of the 600 cell and some new results that are tied up to it. So why minimize potential energy? Maybe the problem dates back to 1900s with a Thomson problem, where he considered the molecules as atoms on a spherical shell that repel with Coulomb law. And in this case, the problem becomes minimization of this potential. I'm not sure if you guys see my pointer, which is Riss energy when S is 1. Now, some problem that was introduced by Stephen Smale with respect to complexity of algorithms is about minimizing the logarithmic energy. That's actually called White's problem, and its earlier version was from 1950s. So we will use the word code to denote a collection of points on a sphere. Now, sphere is our setup, but it can be in other polynomial metric spaces, such as projective spaces or Hamming and Johnson discrete spaces. So electrostatic and electrons in equilibrium, these are beautiful pictures created by my scientific brother, Yangmu Zhao, while he was under the direction of Ed Saf in the 1990s. And you can see 32 electrons in equilibrium and 122 electrons. An interesting game is to know that there are exactly 12 pentagons in such a soccer ball design. Some coding theory found in biology is related to the Thomas problem, which is distribution of orifices on the sphere here. And Thomas asked to maximize spherical caps, equal spherical caps packing, to maximize the radius, if we know the number of spherical caps we place on the sphere. And indeed, if you start increasing that radius, you will see that the caps at some point will become locked in. Now the question is that just a local optimum, or is that the global optimum that we found? Now, codes that maximize that minimum distance, what Thomas is asking, are called optimal or maximal codes. Hence, our choice of terms. Some more codes from biology, orifices, and the puffer fish. It's really fascinating, very nice image. And moving on to the big splash done in the 1985 with the discovery of the buckyballs of carbon-60. Curl, Croto, and Smalley received the Nobel Prize in 1996 for that discovery, and Heath and O'Brien discovered, they got memorable mention. So another, the name fullerenes for these kinds of molecules is actually after Richard Buckminster, or Bucky, Fuller, great architect that lived, 1895 to 1983, that was known for these dome structures. And this is the Montreal Biosphere, Florida fullerene in Epcot Park. And this is an interesting new development. A colleague of mine, a great chemist, Stephen Stevenson, was able to isolate carbon 100. And carbon 100 actually is in this shape. Now, I suspect what he holds is actually not the real thing in nature, is not a tube in the middle, but more like ellipsoid. So he and I are in discussion about exactly if this is points on ellipsoid. This is a nice problem that ETSAF posed to me in the 1990s. So this will open a pretty significant area of research. So that's something that is going on as we speak. There are two Journal of Chemical American Society about what Stephen Stevenson calls Fuller tubes, I think, fullerenes into Fuller tubes. So that is an interesting development. Now, there is a duality structure. Here we have the points with every electron. We associate the points that are closest to it. And then they form the so-called Dirichlet cells. And the vertices of the Dirichlet cells can be considered as separate structure. And we see on the right is carbon 60. And then for 122 points, carbon 240 is the dual structure. So now let's delve into minimal energy problem. Pretty much that was the justification why we consider it. So we will call a finite set on Sn-1, the sphere, unit sphere embedded in the n-dimensional space, with cardinality C being big N. So then we know that the distance between 2 points is really a function of the inner product. So for our interaction potential will be absolutely monotone function in that inner product, meaning that every single derivative is non-negative. So we define the H energy in this form. And as we move on, the interesting quantity that we want to study is the infimum, or the minimum, over these ENHC, that is that H energy. Now, because of continuity that we assume about H, that minimum exists. So the absolutely monotone potentials are interest. I mentioned that. And some nice examples are the Newton potential, which is really that quantity that you see on the slide. The Riss S potential is also very important actually in chemistry. where we are embedded in R3, S is usually chosen to be 6. The log potential is given in this way, and the Gaussian potential is another important potential that we have considered. All of these are absolutely monotone. I should mention that the log potential may be negative, the first quantity, depending on where X and Y are, but that the results are work for that potential as well. Now, spherical harmonics is the next ingredient. And if we consider the homogeneous harmonic polynomials in n variables of degree k, restricted to Sn minus 1, then the dimension of that space is going to be this product of, the binomial coefficient and that fraction. Now that's actually an integer number. We can choose the basis in the spherical harmonics, and with respect to the normalized dimension surface area measure by Graham-Schmidt. Oh no, what happened? Okay. All right, I'm sorry. I think, okay, the Gegenbauer polynomials are tied up to the, I apologize. There is something on my screen that blocks it. A spherical harmonics can be defined through the addition formula. So the Gegenbauer polynomials play significant role, and these are special type of Jacobi polynomials. For the sphere, these will be orthogonal with weight 1 minus t to alpha, 1 plus t to beta, where alpha and beta are n minus 3 over 2. So for the spherical harmonics, that addition formula is essential for bound of energy. And when we look at spherical designs, then the kth moment is given by that quantity, some given a code C, some of the Gegenbauer polynomials with the inner products where X and Y run over the configuration C, then that can be represented by the addition formula in this form, which then of course ends up being something non-negative, okay? And when it's 0, if and only if the sum overall of these X in the code is 0, and we call C a spherical tau design, if the kth moments are 0 for all k from 1 to tau. Okay, that is equivalent to having a quadrature for all polynomials of degree less or equal to tau with respect to the unit measure on Sn minus 1, and that is with the same weight 1 over n. So we want to find good potentials for lower bounds. These will be potentials that are underneath our given potential that we consider H. So f of t will be good candidate if in expansion with respect to the Gegenbauer, it is with positive Gegenbauer coefficients for k greater or equal to 1. All fk Fourier coefficients are actually less or equal, are greater or equal to 0. So we will consider, of course, potentials that are defined in 1, and the convergence is then absolute and uniform, and the energy bound comes into play by considering all of the summations. Now, obviously, we have also added the values when X and Y coincide, so we have to subtract f of 1 times n, and then continuing this, we obtain that the energy can be written with the coefficients along with the mk, and that is then bound below by f0 times n squared minus the value of f at 1 times n. But when you factor out n squared, you get this quantity. So this is important if we want to minimize the energy over that potential F, that good potential F. We really can consider maximizing the quantity F0 minus F of 1 over N over all good potentials, okay? And the good potentials are underneath our H. So let's keep that in mind. The Dosart-Uden lower bound can be formulated in this theorem. A and H will be our good set of potentials that are dominated by H and that have non-negative coefficients, Fourier coefficients, from 1 to infinity. We have C, when C satisfies for some F that equality, this is if and only if when F and H coincide for all of the inner products of a configuration, and when Fk is 0, or Mk of C is 0, whenever K is greater or equal to 1. So again, this poses the linear program, maximize Dosart-Uden lower bound, subject to F being in that space. Okay, but remember that F of t is lesser or equal to H of t, where t is in minus 1, 1. These are infinitely many, actually, you know, overall the interval conditions, okay? So that's infinitely many inequalities. Now, for a subspace lambda, we consider that supremum, okay, over all of these lambda intersection with the good potentials, that quantity. And usually lambda is some span of the Gegenbauer polynomials. And I will give in a little bit some definitions of what lambda may be. Now, this infinite inequality for t, you know, if we substitute with some finitely many or countably many indices or points, tj's, will bring an interesting consideration. And here is the dual programming heuristics. In general, the primal and dual program are related in this form. That's one of these forms. So if we maximize C transpose X subject to AX less or equal to B, and X is a non-negative vector, the dual program is to minimize B transpose Y subject to AT, Y greater or equal to B, Y is greater or equal to 0. Interestingly, I discussed this in my optimization graduate class just maybe a few weeks ago. And of course, it plays so big role in my research and that of my colleagues. So let's go back to what we're trying to do. We're trying to maximize this is about the coefficients subject to the Gegenbauer extension less or equal to H at the nodes Tj. And Fi's have to be greater or equal to 0. Now the dual is to minimize some weights rho j times the value of the potential at the tj's subject to some quantity, which really, if you look at this quantity on the left, that will be a computation of the integral. So we will involve some kind of quadrature formula here. So then we have the complementary slackness conditions for primal objective is equal to dual objective function. We have to have Fi times Wi, which is that slackness here, B0, or rho j times Uj, the slackness here, be also 0. Moving on, the 1nth quadrature rule then is one where F0, which is that integral of f of t times the Gegenbauer weight with some normalizing constant gamma n, be the value of the potential at 1 divided by n plus sum of rho I f of alpha I. And this implies that F0 minus f of 1 over n is equal to sum of rho I f I. So let's give an example of 1nth quadrature rules. So if we have alpha 0 to be 1 through alpha 1, alpha k be the inner product in a configuration that is a spherical tau design, then rho i's are actually the density of each inner product. These will be the weights, and we will have 1nth quadrature rule exact for all polynomials of degree less or equal to tau on minus 1, 1. So this is the given below. So that clearly is a 1nth quadrature rule. Now, ULB space will be such a space such that the intersection subspace, such that the intersection with the good potentials, and there is, I'm sorry, that thing appeared again. There is, I think I'm not very happy with the full screen share. I apologize. So we have WNN lambda h less or equal to n squared times the summation rho I h of alpha I. So I most probably will be helpful to give some examples of such UOB spaces, and these will be coming soon in the talk. Okay, so if equality holds here, then we call lambda a ULB space. So if we have these nice nodes such that equality does hold here as well, then we do have the ULB space. Now, this brings an important notion of Hermite interpolation. And we will, if we have a F, a good potential that is less or equal to H in, am I getting any feedback? Hello?
Yeah.
I hear you loud and clear.
Yeah.
Yes,
Thank
we'll
you.
hear
Thank you so much.
Yeah, we can hear
was,
you. We can see everything. It's good.
Yeah, thank you. Thank you. That was good to know, because I thought I'm lost. So if we have f of alpha less or equal to h of alpha, right? And at some point we meet the potential. And if they are both differentiable, then we have also equality for their derivatives if the point is inside. If the point is an endpoint, then less or equal inequality will hold. So it's kind of necessary to have these not only interpolation of the values, but also of the derivative. So now the examples of UOB spaces come into play. So sharp codes are such spherical designs that they have M inner products between distinct points, and the code itself is a spherical 2m minus 1 design. So let me give you some codes that are sharp. For example, the tetrahedron, there is one in a product, and certainly that is a one design. That's the regular tetrahedron. Then we can have the octahedron, for 6 points, or another name was the cross polytop in general. Also, the 12 icosahedron is another example of a sharp code. And Khan Kumar in 2007 obtained that beautiful result that whenever C is a sharp code, then C is universally optimal. What that means is that C is H energy optimal for any H that is absolutely monotone. Okay, and the idea of the proof of their result is to show that the Hermite interpolant of H to these points for the sharp codes, the inner products for the sharp code is actually in the collection of good potentials, has greater or equal than 0 inequalities. So this actually establishes that the polynomials of degree tau, that set is actually an n norm C, the magnitude of the code C, ULB space, and is the dimension. Okay, so the Levenshtein framework that's coming from maximal codes is that for every distinct, for every fixed n within the Dosart-Geltel-Seidel bounds, there exists a 1 over n quadrature rule that is exact for lambda on the polynomials of degree 2k minus 1. The numbers alpha I are actually coming from this nice property. These are the Gegenbauer polynomials. And no, I apologize. These are the shifted. These are Jacobi polynomials of n minus 1 over 2, n minus 3 over 2 for the odd case. For the even case, they will be n minus 1 over 2, n minus 1 over 2 polynomials. But I will illustrate things with the odd case. So this is a result that we have in our 2016 paper in constructive approximation, that if H is absolutely monotone, and then K and N, the cardinality, are such that big N is greater or equal to the Dosart constants dn 2k minus 1, then the polynomials of degree 2k minus 1 and lower is a UOB space, namely that we have that lower bound. Now this is important moment. The alpha i's and the rho i's do not depend on H. I want to emphasize that. They're obtained by some quadrature rule that is tied up to the degree, to the little n, k, and the cardinality big N. So if the degree is fixed, if k and big N are such that we have this inequality, we can locate the alpha i's and the rho i's uniquely. Okay, and then of course the lower bound will depend on H by the evaluation of these alpha i's. Now this is illustrating very nicely the picture. I think what we have here is 24 points. 24 falls in the third constant, we have three nodes, and these circles are the nodes. The rows are determined uniquely, and what I have here is the Levenstein potential is just associated with the maximum minimum, and it's a negative polynomial underneath from all the way from -1 to the largest node. I think what I have also is the Newton potential. This really good guy is the Gaussian potential, and then the Korevar potential is also an interesting one. I have included it here. So these are some UOB comparisons. For example, the harmonic energy when S is a 1, that's the Coulomb case. So we have various computation for the UOB bound and what the actual energy is. And you can see it's within maybe about 0.2%. Okay, so this is the Newtonian energy in the case when we have 5 through 64 points. The harmonic energies are actually coming from Kohn et al. Computational paper, and little n is 4. So I think I might have misspoke when I said that this is in R3, but it's in R4. So the Gaussian energy comparison is actually here, and you can see the actual energy and our UOB bound. And I should say this is the supposedly, this is computational Gaussian energy. So when you see for 64 points, 408.88, the actual minimum may lie lower, but still above our 408.87. Okay, so this is pretty good UOB that is true for all values of big N over the cardinality of the code. The test functions come into play next. That is actually the values of the quadrature for polynomials that are higher than the I'm sorry, I lost my trend. So coming back to the test functions, the polynomials, this is the definition. J is bigger or equal to the actual degree that we have considerations for. And the improvement, the following theorem is if we have a lambda, a subspace that includes the span of some of the polynomials in some index I, then we have, if the QJs are less than 0, then we can attain an improvement. In other words, improvement is possible if and only if there is test functions that are less than 0. And when I say improvement, that is with linear program. You have to understand that. So these are some codes and the test functions. A very good one is, I don't know why this thing appears on my screen. I apologize. So 424 is a code of 24 points on S3. And this is, we will discuss that a little bit later too, but there, this is a 5 design code. This is what must improve to be the solution of the Kissin number problem. And the first 2 are non-negative, the first 2 test functions. Actually, Boyvalenkov and his students established that the first 2 will always be non-negative. And then there are two negative test functions. They are in red. There is more further down the line. So then we have also the 4120 is a nice, interesting code as well. That is the 600 cell, the password for this webinar. So it's quite well related, the talk that I'm giving. You will see how we can improve, and in some cases, like the N24 and little n4, then this is also the code is obtained by if we consider the lattice, the integer lattice, where the sum of the components of a vector is even, then that's the D4, and C24 consists of the 24 vectors, minimal vectors in the D4 lattice, scaled to the unit sphere. It is the kissing configuration, as I said, and C24 is a 5 design with 4 inner products, distinct inner products, -1, -1/2, 0, and 1/2. The kissing number problem solved by Oleg in 2003 was done utilizing modification of linear programming bounds. C24 is conjectured to be maximal codes, yet not proved, and it is not universally optimal, though. Cohn, Conway, Elkis, and Kumar proved that in 2008. However, it is conjectured to be universally, D4 is conjectured to be, well, I think that conjecture will solve, I apologize. This is kind of, all right. So moving on, then the Levenshtein nodes and weights are alpha1, alpha2, alpha3 are these numbers. You may recall from my picture that was illustrated. These were the nodes of the quadrature rule associated with the Levenshtein framework. And row 1, row 2, row 3 are the weights. And of course, as I showed earlier, the 8th and the 9th test function are negative. So there is room for improvement. Then we can lift the Levenshtein framework, and that is where I start to introduce UOB spaces. So if we consider the span of P0 through P5 included with P8, P9, so these are linear combinations of these, only these Gegenbauer polynomials. In other words, an expansion good potential that has 6th and 7th, these are polynomials of degree 9, but 6th and 7th coefficient, Gegenbauer coefficient are 0. So then we can locate new weights and new nodes so that we have a quadrature ruled holding, and we also have a interpolation solution. So all of the ingredients of the UOB space definition from before are satisfied. Well, what turns out for this particular guy, these are now all positive, the new test functions. So therefore, this is a solution to the full linear programming. Okay, so that's what sometimes is referred to as LP optimal. Arestov and Babenko in 2000 arrived at these nodes weights in the context of maximal codes. They were solving the Levenshtein problem, but that's also for energy bounds, applicable to energy bounds as well. So this is what the optimal polynomial for the 424 code looks like. And then the sufficient condition for UOB is the following. What we really are interested is in the partial products. So if we have some collection T, T1 through Tm, a subset of minus 1, 1, the partial, we can have repetitions in these T's, okay? So we then consider the partial products as the product of T minus T1 to some T minus Tj. So that will be the J's partial product. So the following lemma is crucial for the lifting of the Levenshtein framework. So let alpha I, rho I be a 1nth quadrature rule with these nodes that is exact on a certain subspace lambda. If alpha 1 is greater than minus 1, then the space T or the set T that we consider is repeated alpha 1, alpha 1, alpha 2, alpha 2, etc. Else only take one alpha 1 once. So if we touch minus 1, this will be only a singleton node. Suppose that for each J less or equal to M, which is the cardinality, in that case 2K or 2K minus 1, there exists a Qj such that Qj alpha I is Pj alpha I. The lambda is an n, little n dimension, big N cardinality UOB space. So the proof is in that interpolation formula, what H T1 through Tj is, these are the divided differences, okay, of H, all right? And then F is in AN H, and F alpha I is H alpha I. So that's how we go about the proof of that particular formula. So now let's work on lifting the Levenshtein framework, what we refer to as skip to, add to. So I will talk about the scenario with the Levenshtein framework when the polynomials are of odd degree. So keep in mind the 600 cell. There, the 600 cell is an 11 design. So 2K minus 1 is actually 11. K is 6. Then we consider P0 through P11, added P 13, 12, 13, 14, and 15. All right. So we consider that as lambda and K. Any 1nth quadrature rule that is exact on that lambda and K has at least K plus 1 distinct nodes, okay? And let Bi theta I be the 1n quadrature rule with exactly K plus 1, with K plus 1 nodes on that is exact on Ln K. Let's assume this is the inequality, and then F0 equals to that. So we prove that there is quadrature rule. And what is important here, P2K minus 1, we guaranteed to have a quadrature rule and the UOB space from the Levenshtein framework. So if we add these and we can locate such betas, then we will be able to lift. It's not always possible to lift, okay? In some cases where the original solution is this guy, it might not be possible to extend further things, but many times it is. So how do we go about extension Well, remember, there was, at some point, I wrote to you these orthogonal polynomials with, the 1, 0, the shifted Gegenbauer. They satisfy three-term recurrence relation. So with three-term recurrence relation, we can't really do much. We want a quadrature that skips some of the values. We found out that with five-term recurrence relation, we can do things, okay? And in this case, there is a nice separation between the alpha and the beta nodes. The beta are the nodes from the quadrature that are lifted, okay? So then this is some of the examples where we have things working. So dimension 3, like for these codes, we have improved things. And, the Levenstein, for example, let me go to 424. The new Levenstein will have 5 and the Levenstein is P5, all polynomials of degree less or equal to 5. The new lambda is actually polynomials that are less or equal to 9. Okay, by design, the 6th and the 7th coefficient of the polynomials that we consider will actually have 0 coefficient. Now, let's go to the universality of the 600 cell, which really will tie up everything together. So the 600 cell is 120 points in R4 on the unit sphere in R4. And each X has 12 nearest neighbors forming icosahedron. There are 8 inner products. Okay, I want you to keep that number 8 in mind. So then we would see 600 is an 11 design, but almost a 19 design. Only the 12th moment is non-zero. Okay, so we gotta skip. We have to have a Gegenbauer coefficient that is 0, the 12th Gegenbauer coefficient. Remember that from the general Delsart-Uden, the product of the Gegenbauer coefficient times the moment has to be 0 to have any hope to actually reach the upper bound of the energy for the linear program. Now, Coxeter and Borodsky bounds establish maximal code property for the 600 cell. Andreev found a polynomial of degree 17 that shows that 600 cell is a maximal code, and Dragnev and Boyvalenkov proved the uniqueness of this, having a spherical design, 11 design with 120 points, the uniqueness of the 600 cell. And Khan and Kumar found the family of 17th degree polynomials that prove a universal optimality. Okay, so what they require actually for that, I think it's one polynomial, is that the 11, 12, and 13 coefficient Gegenbauer in their Gegenbauer expansion is actually 0. Okay, with a Lagrange condition at -1. So the partial product method doesn't work for this family of polynomials, okay? So let's now do the lift for the Levenstein framework. The Levenstein quadrature gives us 6 nodes. These are the 6 nodes and 6 weights, okay? And the test functions 12 and 13 are positive, but 14 and 15 are less than 0. So here's what we try. We try to extend by adding the 14th and 15th Gegenbauer polynomial to the span of the degree less or equal to 11. So we were able to find such nodes with this 5-term recurrence relation. beta 1 through beta 7. And then we consider these, this is of this type, the product of all these, you know, the root, so to say. So we verified that Hermite interpolation at these nodes actually works, okay? And we have to verify only for the partial products, these Hermite interpolations, all right? And the new test functions are strictly greater. So this solves the LP in P15. Now, unfortunately, what happens is that a P15, that's not enough. There is more negative new test functions, and we're able to actually do a second lift. That's what's really important. I did this on Maple and located 8 nodes. Remember that we had 8 inner products. Well, they ended up having exactly the same values as the inner products as predicted. And that was kind of my own satisfaction, even up to maybe precision of 50, they coincided. So quite nice. Now, there are actually 2 separate candidates, okay? So we have P17 intersection with the complement of 12 and 13, meaning that the Fourier coefficients 12 and 13, or the Gegenbauer coefficients, are 0, okay? So that's one UOB space. Then another UOB space that we obtain is actually where the 11th and the 12th are 0. Recall that Kahn-Kumar polynomial had 11, 12, and 13, 0, but it had single interpolation at -1. Now, the method, our method actually worked, and it expands a bit the class of potentials for which the 600 cell is universally optimal. Okay, and that's by taking a double interpolation at -1, it was amazing that all of this worked out. So this is the final slide, I think, that shows the famous triangle. So this is the linear program is being solved, and the optimal solutions for degree 17 orthogonal to P12 is actually that entire triangle. Okay, and I had Kahn-Kumar, Bobelenkov, and Hardin named the 3 polynomials. I had to exclude me. So clearly, this is a nice, you know, result that establishes all of the polynomials that are extremal that solve the linear program for the 600 cell. And I want to thank you for your attention.
Oh, thank you very much for a very nice talk. Please, questions and comments.
Yeah, so I can start with a question so that
Sure.
we can get the ball rolling. So first of all, thank you very much. So we finally have a topical presentation about our password, or I guess we finally justified our password. So because I think this is yeah, it's a good
I
justification.
apologize for giving this out. You know, the password did not protect it very well.
Yeah. So this yeah. So right here, this result about 600 cell. So you mentioned. So maybe I didn't understand properly. So you mentioned that you extend applicability of you extend this result of optimality the 600 cell, two more broad cluster potentials? Do you mean
I kind of backed out a little because we don't know whether it is broader, but what we want is actually for this class, maybe that theorem, where is it? Okay. So what we actually proved is there are here these polynomials that are formed from that expansion made out of the partial product. So remember what we have to verify. We have to verify for the Hermitian turbulent at these nodes that they belong to A and H. But they will belong to that class that is dominated by H if these polynomials for the partial products will actually be if this holds for these partial products, if the partial products belong to this class AN, not H, but the partial product as the bound. Okay, so if that's true, then we can combine with the corresponding then we will be able to show also that it will hold true that f of t will be a good potential for H. Okay, so in some sense, what we prove is that this f with these partial products works. Okay, now I don't think we have not delved into whether that broadens the class. We suspect it may, but so it's quite possible that you get not just the absolutely monotone potentials, but maybe a broader class over which the 600 cell is optimal. But we haven't really explored that further. It's we're solving a sufficient condition, let's put it this way, for f of t to belong to A and H.
Right.
But that might be actually also true for other potentials. So, we haven't, of course, one is tied up to these being positive, right? Because
and that interderivatives.
Right. So this divided difference, and you don't even have to have all of the derivatives. This divided difference can be represented as the jth derivative of H at some point.
Yeah.
Or J minus first. I have to look. Maybe, okay, if we have 2 points, is the first derivative. So we have J points, that's the J minus first derivative at some point. And if they are all non-negative, then certainly these guys are going to be non-negative. Right?
Yep.
So,
right, yeah, it makes sense.
Right? I hope that explains it.
Yeah, it would be really interesting, and it totally makes sense that, okay, maybe some values you can allow it to dip the derivative to just become negative a little bit.
Right, but they might not. You might still have these guys represented for that particular potential. The divided differences have to be greater or equal.
Exactly. Yeah. And also, I was wondering if you could maybe clarify. So you talked a lot about C24, right? And this 4-dimensional space, and you listed a lot of configurations, and you said, okay, for this situation, 424, the LP is solved. Yes, exactly. Yeah. Right. So I didn't quite understand. So are these nodes corresponding to C24?
Well, the nodes are analytic. They're not tied up to the configuration. That's the beauty of it. They come from entirely solving the dual problem, if I may say that. So you're looking for a quadrature rule on this subspace.
Yep.
Now this subspace has eight linear, the dimension is 8, right? So since you have a quadrature rule with internal nodes, so you will have alpha I and rho I as parameters, and that will give you at least 4 roots, okay? So 4 nodes. Now, you may have more if you wish, okay? So quadrature, of course, if you allow more nodes, you will have quadrature that exists, but because you'll have more parameters. But this is the optimal quadrature. It turns out that the interpolation problem that you solve for polynomial for H, right, absolutely monotone, is actually also with positive coefficients at these nodes. So that is giving you a solution in that space, okay, in that lambda. However, since the 6th and 7th test functions are non-negative, that will actually be a solution of the linear program in the entire P9 space. Even more, it ends up being a solution for all the span of all polynomials, okay? So maximizing that they'll start using functional, right? F of 0 minus F of 1 over n. So that is why this is LP optimal. We meet many examples where on the first lift, and you reach the promised land. You find the LP optimal. Now, whether you reach the promised land is the right saying in this case, I don't know. Most probably because you can't do better with linear program. Now, what happened with the 600 cell? With the 600 cell, we were able to do better. Okay, so we lifted, we got to these nodes, 7 nodes. Then what we did, we just added 2 extra P16 and P17 to the basis, which allows for 1 node and 1 weight, and we were able to reach the promised land. And we were able to do that with 2 starting points, okay? With a lambda 117 that has 12 and 13 as its coefficients, and a lambda 217 that has 11 and 12 as 0. And the double interpolation was kind of important in this case at -1. That's like you're not really utilizing well your resources, right? You don't need a double interpolation there. Why would you? It's outside, it's the endpoint. But that double interpolation requirement is actually freeing you up a parameter which allows you to go to that expansion and be able to prove things for the inner product, for the partial products.
Thank you. Please, some other questions.
Peter, may I ask a question? Can you go to slide 41?
Slide 41.
Yes. Yes.
Yes.
Can you clarify you say the C24 conjecture to be maximum code but not yet proved. So can you explain the meaning of maximum code here?
Maximal code is to maximize the minimum distance. So if you have 24 points on S3, and you maximize the minimum distance, the conjectured one is the best packing pretty much. is that C24 is the one, what I described above. But it is not, you know, yet proved. That is a
So we know this.
conjecture.
Okay, so the 60 degree can be a 10, right? Because we know the kissing configuration. So that may be larger angle, more than 60. So let me explain again. So what you're saying is that you have a 24 point on S3, right? And they want to mimic the angle. So we know it's already kissing configuration, right?
It is.
So we know the
That's
angle
correct.
at least is 60 degree apart for each pair of point. So that means if you say this is open, that means that might be more than 60 degree among other 20, right?
Might. It's believed that it is exactly 60 degree, but it might.
Okay, okay.
Yeah.
Got you. So we can prove the 20.
What I think, and I think Oleg is among the participants, what I think was if we have a kissing number, this is good. But if we have, you know, kissing number with 25 is not working. That's what he proved.
Yes.
I don't know if he wants to elaborate a little.
Okay, thank you. I think
that's really his domain.
Okay, okay. Thank you for explaining. Yeah.
Thank you.
Yeah.
Please, some other questions? Okay, when there is no other questions, maybe we can stop recording and maybe some people can ask some a bit later.